The topic of this segment is GPUs, graphical processing units. I'm going to show an example of doing a convolution using a GPU in Julia. So the actual application is probably not particularly important, but we are going to take this Julia logo right here, and we're going to blur it. So here's the logo. You can see it being blurred, right? But that's not the important part. Probably the important part is to see for yourselves the power of a GPU. So I'm going to demonstrate this in Julia right here. Let's focus on the time. I'm going to compare a CPU code with a GPU code. And so let's go ahead here and execute the blurring on a CPU. And it took 257 milliseconds. Let's just do it again just to see. Oh, it's about the same. Yep, always about, 256, 257 milliseconds. Now I'm going to run the very same code, same blurring. I'm going to do it on a GPU. Okay, and so look at that. 2 milliseconds, 2.2 milliseconds. So, that one was a little bit more, 45, but that seemed to be a fluke, 2.2, 2.2. So about 2 milliseconds usually. And do you see that? It's 100 times faster on the GPU than the CPU. So what's going on here? What's this all about? And what is the research problem that Julia is trying to solve? Well, let me start with that second question. So with Julia, we're trying to make it that you don't have to learn a new language to be able to run on a GPU. So this is the code portability problem. And it's pretty much a holy grail of high-performance computing, computer science, that the user just decides where the data is going to live, and the very same code that calculates the convolution should just work. These aren't library calls. These are actual functions that are written somewhere here, down here. I can try to find it if you'll give me a chance to look for it. So here's the convolve2d function. And this function, this is the basic math of a convolution. You take the data, you multiply it pointwise by a filter, and you add it all up. Okay, we can look a little bit at the end of this segment what some of the specifics of the Julia implementation are doing. It's pretty simple, really, though there may be some commands that might look a little funny. But basically, if you want to do a convolve2d, you just simply apply this CU function. CU stands for CUDA, which is the NVIDIA language for doing GPU computations. You take the CU, that will put the image on the GPU. The filter is the same filter, and the range, that's going to be the interior part of indices, will also send over the GPU for convenience, and then we're just going to run the code. I didn't do it over here because I wanted to not count the timing for the movement, just for the computation, but it's the same basic idea. So let's step back a second, talk about GPUs. GPUs are made by a number of manufacturers. I think it's fair to say that the NVIDIA GPU is probably one of the most popular ones right now. The NVIDIA, here's some pictures I just Googled the pictures of NVIDIA GPUs. GPUs started out life being particularly useful for gaming, for graphics processing, hence the name. Somewhere along the line, people realized that the very same horsepower that's needed to computate for graphics turns out to be really, really useful for certain kinds of computations. And specifically, it's very regular computations. So for those of you who know about matrices, matrix multiply is something that GPUs can do really, really fast. So if you're multiplying little matrices and lots of them, this is the sort of thing that, for example, is happening in machine learning algorithms, then GPUs just really scream, and hence they're very popular for AI applications. Convolutions have a very similar character. They're very regular. I suppose you could imagine that if you had not a computer, but you had a bunch of people, and you asked them to each convolve an image, you could easily kind of choreograph the various people that you have, because it is so parallelizable, so regular, so easy. That's where the GPUs shine. They don't do very well at general purpose computations, and that's where the CPU kind of has the advantage. But when you have these very, very regular, computationally intensive computations, then the GPU does very well. So NVIDIA is one major manufacturer. The AMD is another one. I just Googled AMD GPUs, and here are some pictures of the kinds of boards that have come up. And Intel is very much in the act with the laptops, and here you can see some Intel GPUs. So these various GPUs are what's accelerating AI and lots of other numerical applications. So let me get back here to this code. I said I would kind of show you a few aspects to this code. I didn't really want to go into great depth, but let me just mention that we use a few things. For example, Julia has a Cartesian index function so that you could directly index into arrays with indices -2 and -1 and 0. So here's a kind of 5 by 3 window centered at 0, 0, and I think you could all guess what these indices are doing. So to understand the array here, let me remind you, the 2 means it's a two-dimensional array, and the entries are tuples of integers, and you can see that. So these are the various indices in this 5 by 3 array. And we wrote below a neighbors function, which here for, if you have a sort of 3 by 3, then the neighbors are in the x direction -1, 0, and 1, and in the vertical direction -1, 0, and 1. So let me just show you a few pieces of this. Again, I didn't really want to go into too much detail. Here is the Julia logo being downloaded. Here's the Gaussian filter that I think you'll all recognize. So this is a function of x and y, and by default we'll use sigma, but you can change it. So by default we can use sigma to be 1/2. So you could see that this is the usual Gaussian function right here. And we're also going to allow ourselves to call this Gaussian function with these indices, like the ones you saw up above. So this basically lets you use indices instead of directly using x and y, just as a convenience. Okay, and then we're going to compute the Gaussian filter, and here you can see we're going to use an S matrix, which is a static matrix. This is a performance hack. I don't think I need to go into this too much, but this will calculate the Gaussian filter in the normalized way. Here also we've got some neighbors, but let me go down to the Convolve2D just to take a look at it. Basically, we get the neighborhood of every point, and we're going to compute this static matrix. And I just want to point out some of the pieces, because you may not be so familiar with these ideas. So we have our image, it's in A, and we don't want to make a copy because copying data is very, very expensive. So, in fact, memory movement, I've seen in other computer science classes, people will count operations like adds and multiplies. But actually, memory movement is a much more significant matter for most computers. So here what we're going to do is, instead of making a copy of A, we're going to take a view, which means we kind of have this like 3 by 3 submatrix of A, but without making a copy, and we load it into a static matrix. So, and here's the math. Okay, and so when we do that, you can sort of see what happens when we filter. We'll do some padding, and the thing that I want to show you most is how it's called, because this is where the GPU is most useful. We're going to do this with a broadcast. So what this basically says is we're going to apply this Convolve2D, which is defined at a point. We're going to do it at every interior point in the image. Okay, so you can go through this yourself. I'll post this notebook. You will need a GPU, a machine with a GPU, if you're actually going to run this thing. But again, I want to conclude with the most important piece, not the Julia code. We could kind of go over that separately. But the real point that the same code runs on a CPU and a GPU, no special languages. You get that factor of 100 speed up that you hope to get from a GPU. And the main key difference, I mean, there's some devil in the details, but the key difference is the CU command, which is going to move the data from the CPU, the central processing unit, down to the GPU.